Welcome everybody. This is a short version of my video for proving Euler's famous identity, meaning that if you plug in a real number phi times the imaginary unit I into the complex exponential function to be defined yet, then you end up with the cosine of this number plus I times the sine of this number. Now this proof is for people who haven't heard about convergence a lot, or for physicists who don't care about convergence or the finer points of math. Sorry, I'm being mean. So I only present the main facts so that you get the main idea without concerning myself too much with mathematical intricacies of convergence and some finer points. What you need to know is the Taylor series expansion of the real sine and cosine functions, which is presented here. Sine can be written as this power series x minus 1 over 6 times x to the 3 plus 1 over 120 x to the 5 and so on, and in general here minus 1 to the n, then an odd number factorial and x to this odd number. The same for the cosine, but with even exponents and even numbers here in the factorial. Okay, this part here we skip. And what you absolutely need to know is the definition of the complex exponential function. You get this if you take this power series. You take 1 over k factorial times z to the k and take the series of this. And this guy here converges for every complex number z. That's a fact that we're not going to prove, but that we're going to use. So now to prove this famous identity, we of course start with the definition of the complex exponential function and plug in phi times I for the number z. And then I end up with this, and this here can be written as phi to the k times I to the k. Now we stated as a fact that this complex series converges for every entry, especially for this entry here. And now another fact is that then I can split up the limit into the limit of the real part of this series plus I times the limit of the imaginary part. This is done here, with the additional observation that if I take the real part of this series, then only the even exponents here matter, because if I have an odd exponent, for example 1, then here I have I. The real part of I is 0. Same for the real part of I to the 3. I to the third power, which is minus I. The real part vanishes. So if I take here the real part of this limit, then I only need to use even indices. Same here, if I take the imaginary part of the limit, I only need to consider odd indices, because for even k, for example, k equals 0, this is 1. The imaginary part of 1 is 0. If k equals 2, this is I squared, which is minus 1. The imaginary part is 0. So all the imaginary parts here vanish if I have an even index. This explains this reduction in the indices here. And now every even number can be written as 2 times m being a natural number or 0. So I do that here. And then I have to sum from 0 to infinity over a new index m, where I write here the k as 2 times m. The same here. I take the series starting with m equal to 0 up to infinity and write all these k's as 2m plus 1, because every odd number can be expressed as an even number plus 1. And then here's a very easy but important observation. The real part of this guy here, I to the 2m, is minus 1 to the m. Because this here is I squared to the m, which is exactly that. So the real part is exactly this number. And as explained before, the imaginary part vanishes. And the same here. The imaginary part of I to an odd exponent is simply minus 1 to the m, because here I to an odd exponent can be written as I squared to the m times I. This again is minus 1 to the m times I. So the real part here is gone, and the imaginary part gives me this alternating plus and minus 1. And now I actually end up with the Taylor series for cosine and sine. If you take a look at that and replace m by n, then you have here the Taylor series for cosine and for the sine. And this proves, by omitting some finer points, that this complex number here is exactly cosine phi plus I times sine phi. And whenever you're talking about this equation, you need to include this very, very special corollary. Corollary means easy consequence of a proven fact, which connects three of the most famous and fundamental constants or numbers in math, namely Euler's real number, 2.718 and so on, which comes up in a lot of branches of math, but especially when solving differential equations or describing growth processes. Then pi, you all know where pi comes from, and the imaginary unit I. If I combine these three in this way, then I end up with -1, which is almost unbelievable if you haven't heard about this, because E is irrational, even transcendental, which is a stronger condition than irrational. Pi is irrational, even transcendental, and I is not even real anymore. But if I combine them like that, I end up with the real number -1. This is completely mind-blowing. But if you know this formula, Euler's identity, the proof is trivial, because you simply have to plug in pi for your angle, and the cosine of pi is -1 and the sine of pi is 0. So that's it. But as you see here, to prove this formula, you need a lot of background math. So it's not as trivial as it seems, but it is certainly one of the most beautiful equations in all of math. Okay, that's it. A short version of this proof, which contains, I think, all the main points without the intricacies of complex convergence. I hope you enjoyed the video. Thanks for watching, and come on. And hopefully I'll see you later.